So we're going to be talking about something that we haven't done in a while, and that's limits. But this time we're going to be approaching limits from a different idea. Instead of having x approach a specific number and see how close it can get. So if x was approaching 5, we'd see how close to 5 you can get, but not exactly 5. Now we're looking at limits to infinity, either negative infinity or positive infinity. You know what that really is asking? What is the end behavior of a graph? You might have remembered this from talking about polynomials in Algebra 2 or pre-calc. When you look at the end behavior, sometimes you have both ends going up, both ends going down, or opposites, depending upon the degree. Well, also with rational functions, we looked at this. What's the end behavior? And there is another word which basically tells us the end behavior or tells us the limits as we go towards infinity or negative infinity. Horizontal asymptotes. Horizontal asymptotes tell us what happens on the ends of the graph. There's lots of graphs where they will both go up, or one goes down and one goes up. They're just going to infinity or negative infinity. There's no limit there. Remember, infinity is not a limit. A limit must be a specific number. However, when you have a horizontal asymptote, that means the graph is getting closer and closer to one specific number, just like a limit. And if you recall, finding horizontal asymptotes all depends on finding the degree, the highest degree, of the numerator and denominator. If the denominator has a higher degree, we have a horizontal asymptote at 0. If their degrees are equal, we just look at the coefficients of those highest degree terms. And then finally, if the numerator has a higher degree, there is no horizontal asymptote. This means that the graph is going up towards infinity or down towards negative infinity. Technically, this also means there'll be a slant asymptote there. This has nothing necessarily to do with limits, but will help us to graph in the very next lesson. So we'll go back and we'll review slant asymptotes either in class, or I'll send you a video on how to remember how to get the slant asymptote. But here's some examples of limits. So these 3 examples right here, when we're doing it, we're not going to say what's the horizontal asymptote. We're going to say what is the limit as x approaches infinity. As this gets infinitely large, the only terms we need to worry about are the highest degree terms. Why? Well, for a quick perspective, infinity squared is so much larger than infinity that, believe it or not, this portion of the denominator is irrelevant. It is so fractionally small compared to x squared, they are basically not important. So when we look at this, yep, the denominator has a greater degree. In fact, if you took this and just looked at those highest degrees and then simplified a little bit, you get 4 over 3x. And we know that as x approaches infinity, the denominator is infinitely large compared to a small number up top. That's going to be 0. Folks, you don't really need to write this in, but if it helps, think it through or write it down. Technically, this would just be 0. For the next example, once again, we're going to look at the highest degree terms. And when we simplify 4x squared over 3x squared, we have a horizontal asymptote. No, I mean a limit as x approaches infinity. Or are they the same thing? Finally, for the last one, I'm looking at the highest degree terms. When I simplify this, 4x cubed over 3x squared, technically I could simplify that to 4x over 3. Divide out 2 of those x's. When x is approaching infinity, that gets infinitely large. There we go. And we all know this means it does not exist. So, what happens if we did this towards negative infinity? Would that make any difference? Not for 0. It's still infinitely small. Not really for this number. The x's divide out. But if we did it down here, it would change the direction that graph goes. It would change this so that I would get negative 4 infinity over 3. That would be approaching negative infinity. It still doesn't exist, though.